Hello students, we are going to discuss a new chapter today, that is mechanical properties of solid. In this chapter, we will understand what is pressure, the Pascal's law, the application of Pascal's law, that is hydraulic lift, then the Torricelli's experiment to measure the atmospheric principle, then we'll understand about the Archimedes principle to learn about buoyancy, then the upthrust, then the types of upthrust, the effects, then we will see principle of flotation, then we'll understand about two types of flow, that is streamline and turbulent flow, then we will see the equation of continuity for the flow of fluid through the pipe, then we will understand the Bernoulli's principle, its application, then we'll understand about the dynamic lift and Magnus effect, the stickiness, that is viscosity of fluid, the Stokes law and terminal velocity. Because of the viscosity, there will be friction. The force of friction will be given by the Stokes law, and the velocity of any object in given fluid will be terminal velocity. Then we'll understand about the turbulence, the surface tension, and at the last we will understand about drops and bubbles, the formation of drops and bubbles, excess pressure inside them, etc. So let us begin. First of all, we'll understand some properties of fluid. Any substance that can flow is called fluid. Thus, both liquids and gases are fluids. They have no definite shape, but they take the shape of the vessel that contains them. They have very small resistance for shearing stress, that is, a little force along the tangents to their surfaces will bring them in motion. The shearing stress of fluid is nearly 10 power 6 times smaller than the shearing stress of solids. The gases are highly compressible, but for liquids, external pressure causes a very small change in their volumes. Liquids have free surface of their own, while the gases does not have any free surface. The gases are highly compressible and liquids are incompressible, their volumes. Now, pressure. The normal force acting per unit area is called pressure. It is a common observation that it is easier to cut vegetables with a sharp knife than with a blunt one. It is because the blunt knife has wider surface area. As surface area is more, the pressure will be less. But the sharp knife has the lesser surface area, so it will apply more pressure. The excess area of contact decreases the impact of force. This brings in the picture the concept of pressure. The pressure is equals to force upon area. The SI unit of pressure is Pascal or Newton per meter square. The other very useful units of pressure are atmospheric pressure. This ATM is atmospheric pressure. One ATM is equals to 1.013 into 10 power 5 Pascal. The another unit is torr. 1 torr is equals to 133 Pascal. The atmospheric pressure is also measured as the length of the mercury column, that is 1 mm of Hg is equals to 1 torr. The other unit for atmospheric pressure is 1 bar is equals to 10 power 5 Pascal is nearly equal to 1 atm, and 1 millibar is equals to 100 Pascal. For example, there is one object. The mass of the object is, let's say, 5 kg. It is kept on a surface. The sides of the object in contact with the surface are 5 cm. This one is 2 cm. And this height is also 5 cm. Now, there will be a gravitational force acting on this object. So, due to the gravitational force acting on this object will apply some pressure on the surface. Let us find the pressure for the given situation. The pressure is force upon area, but the force responsible for the pressure is the force perpendicular to the surface. Here the gravitational force acts perpendicular to the surface, so pressure is F perpendicular upon area. In this particular case it will be mg upon A. Now, given mass of object 5 kg, g 10, area will be, the area of contact is 5 cm and 2 cm. So 10 into 10 power minus 4, because we want it in meter square. So pressure will be equal to 5 into 10 power 4 Pascal. Now, if we change the surface area in contact, then the pressure will also change. For example, if it is kept in such a way that this 5 cm and 5 cm are in contact with the surface, then the force will remain same, but the area will change, so does the pressure. So we can write pressure is directly proportional to force, and for given force, pressure is inversely proportional to area. For any case, if we want to find the maximum pressure, will be equal to, for the given block the weight will be fixed, so force is fixed, so P max will be equal to A minimum, and the minimum pressure is equals to force upon maximum area. In this particular case, the minimum area of contact is when this 5 and 2 are kept in contact, and the maximum area will be when this 5 cm and 5 cm sides are kept on surface. For 5 cm and 2 cm, this area is minimum area. So the pressure will be maximum. Let us find the minimum pressure. The minimum pressure will be force upon maximum area. The force will be mg, that is 5 into 10 divided by the maximum area, that will be 25 into 10 power minus 4. Simplify this, we will get the minimum pressure as 2 into 10 power 4 Pascal. So the maximum pressure is 5 into 10 power 4 Pascal, and the minimum pressure is 2 into 10 power 4 Pascal. Some practical applications. of the pins of the pressure are the pins and the nails. Push pins or the nails we can easily penetrate into the board, soft board, or into the wall because they both have small area. So for even small amount of force, pressure is very large. The other example that is used in medical is the sharp needle of syringe. That is syringe of an injection. It can easily penetrate the skin, but wider object like ruler can't do so. It has lesser area, so pressure will be more. The other example is it is difficult for a man to walk on sand while camel can walk easily on it. In spite the fact that camel is much heavier than man. This is because camel's feet have larger area. Area is larger, so pressure will be less. So it can walk easily on sand. So these are some practical applications of pressure. Now let us see one example. A room has floors of dimension 4 meter and 5 meter and height of 3 meter. We want to find the weight of air in the room at 20 degrees Celsius and the total downward force on the floor surface due to the air pressure at 1 atm. First, we will find the weight of air. The volume of air in the room will be equal to the volume of room, because we have just seen the property of fluid, they take the size of a container. So that will be 4 into 5 into 3. So volume will be 60 meter cube. Now mass is equals to density into volume. So density of air is 1.2 into 10 power 1.2 kg per meter cube, keeping it in SI unit, into the volume is 60 meter cube. So the mass will be 72 kg. Weight of air will be equal to 72 into 9.8, that is mg. That will be equal to approximately 705.6 Newton. This will be the weight of air inside the room. Now we want to find the downward force F, that will be equal to pressure into area. As we know that pressure is equals to force upon area, so downward force due to air pressure will be equal to pressure into area. The atmospheric pressure is 1.013 into 10 power 5 Pascal or Newton per meter square, and the floor area is 4 into 5, that is 20 meter square. So the force will be approximately equal to 2 into 10 power 6 Newton. Now let us brush up our concepts of density. Density is defined as mass per unit volume. it is denoted by rho. So rho will be equal to mass per unit volume. The SI unit of mass is kg and that of volume is meter cube. So SI unit of density will be kg per meter cube. The CGS unit is gram per centimeter cube. The density of water at 4 degrees Celsius. Density of water at 4 degrees Celsius is maximum, that is 1000 kg per meter cube, and in CGS unit it is 1 gram per centimeter cube. The density is scalar quantity. The relative density. Relative density is the ratio of density of substance to the density of water at 4 degrees Celsius. We are taking density of water at 4 degrees Celsius because at this point the density is maximum. It is unitless because density divided by density will be cancelled out. So it is unitless and dimensionless. The relative density is density of object divided by density of water at 4 degrees Celsius. Now, note that relative density of any object is equals to density of object in CGS unit. How? Let us see with an example. For example, the relative density of any object is given 2. We want to find the density of body. Relative density 2 is equals to density of body upon density of water. If I want the density of body in CGS unit, I have to put density of water also in CGS unit. The density of water in CGS unit is 1 gram per centimeter cube. So the density of body will be 2 gram per centimeter cube. If I want the answer in kg per meter cube, that is in SI unit, then we have to just multiply the relative density by 1000. So density of body will be 2000 kg per meter cube. For example, a body having relative density 5, then density of body will be 5 gram per centimeter cube or gram per cc cube or 5000 kg per meter cube. So from the relative density we can find the density in SI as well as CGS unit. Now let us see some examples on density. In this example, two liquids having densities D1 and D2 are mixed in such a way that both have same mass. We want to find the density of mixture. Let's say mass of both the liquids is M. So M1 is equals to M2 is equals to M. Density D1 is equals to M1 upon V1, that is equals to M upon V1, and density D2 is equals to M upon V2. When they are mixed together, the mass of the mixture will be equal to 2m, and total volume of mixture will be equal to V1 plus V2. So let us find V1 and V2 from this equation. So V1 will be equal to M upon D1 and V2 will be equal to M upon D2. So the density of mixture D will be equal to, density is mass upon volume, total mass is 2m, total volume will be V1 plus V2, that is M upon D1 plus M upon D2. So D will be equal to, this M will get cancelled out, 2 divided by D1 plus D2 upon D1 D2. So the density will be 2 D1 D2 upon D1 plus D2. So this will be our answer. If in the same question it was given that they are mixed in such a way that they have same volume. So let us see that case. Let's say both are having same volume, V1 is equals to V2 is equals to V. Density D1 is equals to mass M1 upon V and D2 is equals to mass M2 upon V. So M1 will be equal to D1V and M2 will be equal to D2V. The mass of mixture will be equal to M1 plus M2 and volume of mixture will be equal to V plus V, that will be equal to 2V. So the density of mixture will be equal to total mass, that is M1 plus M2, so D1V plus D2V upon total volume 2V. So this will give us the answer D1 plus D2 upon 2. So if the mixture has same volume of substances, then the density will be D1 plus D2 by 2. And if it has same mass of participating substance, then the total density will be 2D1 D2 upon D1 plus D2. In this example, a liquid mixture of volume V has two liquids as its ingredients with densities alpha and beta. If density of the mixture is sigma, then what is the mass of first liquid in the mixture? We want to find the mass of first liquid having density alpha in the mixture. Let's say the mass of liquid having density alpha is M1 and mass of liquid having density beta is M2. The total volume here is V. And density of mixture is given sigma. Now, total mass will be M1 plus M2 we can write the density of mixture is equals to sigma is equals to M1 plus M2 upon total volume, that is V. So we can write V into sigma is equals to M1 plus M2. So mass of second liquid will be V sigma minus M1. Now sigma is equals to total mass upon total volume. So that will be equal to M1 plus M2 upon total volume. Volume is given by mass upon density. So volume of first will be M1 upon alpha plus M2 upon beta. But instead of M2 we can write V sigma minus M1. So sigma will be V sigma minus M1 plus M1 divided by M1 upon alpha plus V sigma minus M1 upon beta. This M1 will get cancelled out. So sigma will be equal to V sigma divided by, take the LCM. So M1 beta plus V sigma alpha minus M1 alpha. This sigma will get cancelled out. So we can write M1 beta plus V sigma alpha minus m1 alpha is equals to V. So m1 into beta plus beta minus alpha, that will be equal to V minus V sigma alpha. But this will be multiplied by alpha and beta. So this will be V alpha beta. So m1 will be equal to, take the V alpha common, into beta minus sigma divided by this beta minus alpha. So this will be our final answer. This will be the mass of first liquid having density alpha. Now let us understand the Pascal's law. Before Pascal's law, before the statement, let us see one experiment. There is a fluid. It is almost incompressible. The meaning of incompressible is that its volume cannot be changed. Whenever you apply force, its density will not change. It will start suddenly moving due to the application of that force. So such incompressible liquid is kept in this container. There are three outlets we can see. The diameters of these two outlets are same. Diameters and length are same. Now, initially when this is at rest, then the level of liquid in all three the outlet will be same. The liquid will be at the same level. Now we are applying our external pressure with the help of piston. Piston is rod-like structure. It will create the vacuum over here so that we can easily compress this liquid. Now when we have applied some pressure with the help of this piston, the liquid level in this outlet will decrease. Let's say it reaches up to this level. Now this decrease will be result in the increase of the water level in two of the arm. So when we have applied some external pressure, the liquid level in the side outlets will increase, and as the diameters are same in both the outlet or both the side tube, their height will also be same. So the increase in height will be same for both the outlets. Now this is due to the Pascal's law that states that whenever the pressure in confined fluid is applied, that is pressure in confined fluid at rest. Focus on the words. The fluids should be confined. That means it should be in a closed container, not in open, and it should be at rest. The pressure is transmitted undiminished and equally in all the directions. Confined means it is contained in a body, in a closed container, and the fluid should be at rest. If we apply the pressure, it is transmitted undiminished. The meaning of undiminished is, if we have applied a pressure of 10 kilopascal here, then 10 kilopascal will be distributed in all the direction. This will not divided. We cannot say that 5 kilopascal in this arm and 5 kilopascal in this arm. It will be transmitted equally, undiminished, and it will be transmitted in all the directions. So pressure applied in confined fluid at rest is transmitted undiminished and equally in all the directions. That is Pascal's law. Let us see how we can prove it mathematically. Imagine a small element of fluid in the shape of a right-angle triangle prism. It is shown in this figure. The chosen element is actually very small in size so that all its points lie at the same depth inside the liquid. Therefore, the effect of gravity is same at all the points. For clarity, the element has been enlarged in size. It is very small, so the gravitational force acting at all the points are very same. The forces exerted by the rest of the fluid on different surfaces of the fluid elements are: on the surface EBCF, force F1 is acting. On the surface ABED, force F2 is acting. And on the surface ACFD, force F3 is acting. This forces F1, F2 and F3 are due to liquid. Now, the forces exerted on the surface ABC and DEF from this side and from the back side of the object, ABC and DEF, they are in the opposite direction and they will cancel out each other. It is because the fluid element remains in equilibrium. Thus, the horizontal forces exerted at the opposite faces must be balanced. It means that for a liquid at rest, the pressure is same at all points in horizontal plane. Thus, applying the laws of sine, let's say this angle is theta. So, if we apply the laws of sine, we can write F1 upon sine theta is equals to F3 upon sine 90 is equals to F2 upon, this angle will be sine 90 minus theta. So, F1 upon sine theta is equals to F3 is equals to F2 upon cos theta. So, we can write F1 is equals to F3 sine theta and F2 is equals to F3 cos theta. If A1, A2 and A3 are the surface areas of sides AB of the sides BECF, BADE and ADCF respectively. That means this area is A1, this area is A2 and this area is A3. Then we can write that A1 is equals to A3 sine theta and A2 is equals to A3 cos theta. Let's say this is equation 1, this is 2, this is 3 and this is 4. From 1 and 3, if we divide 1 and 3, then we can write F1 upon A1 is equals to F3 upon A3. And from 2 and 3 we can write F2 upon A2 is equals to F3 upon A3. But force upon area is the pressure, so P1 is equals to P3 is equals to P2. Hence, Pascal's law is proved. That means the pressure at all the surfaces are equal, and the pressure applied is transmitted equally and undiminished. It again proves that pressure is scalar quantity because it is same in all the directions, so it is independent of direction. Now let us find the variation in pressure with depth. For this we have taken a container in which a cylindrical object is kept. Let us find the pressure at 2 points 1 and 2 whose levels differ by h in a fluid at rest. Let P1 is the pressure at surface 1 and P2 at the surface of pressure 2, and the height above P2 is h. Now imagine a fluid element in the shape of cylinder. If A is the area of top and bottom, they are having same area. So let's say A is the area of circular part of cylinder. Then force acting at this point will be equal to, force is equal to pressure into area, and force acting at this point will be equal to P2 into area. This is the normal force experienced by the top part of the cylinder, and this is the normal force experienced by the bottom part of the cylinder. Now the fluid remains at rest, so the resultant horizontal forces should be 0. These are the forces applied by fluids, so it should be 0. The force F2, which acts upward, should balance the two downward forces, that are mg and the F1. Because fluid is at rest, so this cylinder is also at equilibrium. So we can write F2 is equals to mg plus F1. If rho is the density of the fluid, then F2 is equals to F1. We have considered this a water cylinder, that is, it is not actually solid body, but we have considered it a water shaped cylinder. Then M can be written as density into volume into G. As density is equals to mass upon volume, we can write mass is equals to density into volume. So F2 will be equal to F1 plus density. Volume of the cylinder will be area into height into G. So F2 minus F1 will be equal to rho A H G. Divide both the side by area. So F2 upon A minus F1 upon A will be equal to rho Hg. But force upon area, this is normal force acting at bottom upon area of the circular part, and this is the force acting normal on the top surface upon area. So this will be the pressure P2 minus P1 is equals to rho GH. So the pressure difference between these 2 points separated by height h will be equal to P2 minus P1, and that is equal to rho GH. Here it is very important point to note that h is the height of liquid column above the point. So we don't have to worry how much depth of liquid is there below this point. If we want to find pressure at point 2 and height of liquid is h, then the pressure will simply be rho gh, where h is the height of liquid above the point of interest and not the below point of interest. Now, if we shift point 1, if point 1 is the top of the liquid surface, then which is open to atmosphere, then it will have additional atmospheric pressure. So P1 will be equal to P atmospheric. So we can write P2 minus P atmosphere is equals to rho GH. This is the gauge pressure. At depth h, and if we want the absolute pressure P2, that will be equal to P atmospheric plus rho gh. This will be the absolute pressure. So at any point, if we consider the pressure of atmosphere, then it will be absolute. If we do not consider the pressure of atmosphere, that means if we subtract it, then it will be the gauge pressure. Now, let us see the hydrostatic paradox. Consider 3 vessels of different shapes but having same base area. They are filled with the same liquid, that is density of the liquid is same, and the liquid is filled up to same height h. Then the pressure at the bottom of all the 3 surfaces will be equal to P atmospheric plus rho gh. So the hydrostatic paradox is the liquid pressure is same at all the points at same horizontal level. If we have considered the points at the base, given all 3 containers are kept at same level, then at the base, as they are at same horizontal level, pressure will be same. If we consider other point P, which is also at same horizontal level, then at this point P, the pressure will be same in all 3 containers. Now, regarding to this, we want to compare the force at the base of all 3 containers due to water, given the base area is same for all 3 containers. If we use the formula, pressure is equals to force upon area. The pressure at the base is same, that is P, and area of all the containers is same. So we can say force is same for all the containers. That means the force acting at base is same. The force acting at the base will be simply the gravitational force, that is equals to mg of the liquid. G is same, so we can say that mass of all the liquid kept in all 3 containers are same. So from this we are saying that mass in all 3 containers are same, but it is clearly not the case, because as the size of all 3 containers is different, the liquid filled will be different, so the mass of the liquid will be different. So what is correct? Force is same because pressure is same, or the force is not same because pressure is not same. Let us see in the depth. Here the pressure is applied on the base as well as on the walls of container, and the pressure always acts normally to the container. In this case, these two forces will cancel out each other, so there will not be any effect of this pressure on the downward force. So here the downward force will be equal to the pressure into area. But let us see this case. Here the pressure will be acting along this direction, normal to the surface will be along this direction. So if we divide this pressure will create a force. So if we divide this force into components, the components will be, one will be horizontal and one will be in upward direction. For the same here, one will be in horizontal direction and one will be in vertically upward direction. These two horizontal forces will cancel out each other, but this upward force will not cancel out each other. So in this case, there is some downward gravitational force and some force is due to the pressure in vertically upward direction. So net force in downward direction is decrease in this case. Now let us see the third container case. Here the forces acting on the walls will be perpendicular, that will be in this direction. Again, if we divide the forces exerted due to this pressure, then this will be horizontal component and this is vertically downward component, this horizontal component and vertically downward component. These two horizontal forces will cancel out each other, but these two downward forces will add it up with the gravitational force. So the F net will be equal to mg plus F vertical forces. So here net force in the downward direction is more than mg. That means here the mass is more. So whenever we are finding the force with this formula, we are just finding the force on, we are just considering the force on bottom surface only. So our hydrostatic paradox is correct, that pressure at all the points remains same, but the force will not be same. The force will depend on the shape of container. Now let us see one example based on that. Find the pressure exerted below a column of water open to atmosphere at depth of 20 meter. Let's take a container which is open to atmosphere. We want to find the pressure at depth of 20 meter. At this point, the pressure will be due to this water column, let's say this is P, plus the additional pressure, that is atmospheric pressure. So pressure total or net pressure will be equal to rho GH plus atmospheric pressure. The net pressure will be, density of water is 1000 kg per meter cube into G, let's say 10, and height is given 20, plus atmospheric pressure is 1.013 into 10 power 5 Pascal. So this will be 2 into 10 power 5 plus 1.013 into 10 power 5. So the net pressure will be 3 into 10 power 5 Pascal approximately. So we just have to consider the height of liquid column above the point of interest. If this container is said to be closed, then we have to consider the pressure of the air column over here, which will be given, or if it is given vacuum in this place, then at this point pressure will be 0. In this example, the U-tube in the figure contains two different liquids in static equilibrium: water in the right arm and oil of unknown density in left arm. Given this length is 135 mm and this D, this height difference is 15 mm. We want to find the density of oil. To solve this kind of problem, first we have to choose a level. Choose a level above which all the heights are known, and at this point the two liquids should intersect, or the point should be separating the two liquids. As this whole system is in still equilibrium, that means the pressure at points A and B will be equal. So pressure at point A is, as this U-tube is open, atmospheric pressure plus pressure due to the oil column of unknown density, let's say rho. So pressure due to this oil column will be density of oil into G into height of oil column, that will be L plus D. And pressure at B will be equal to, due to atmospheric pressure plus, at this point atmospheric pressure will be acting due to the water in this column of length L. So density of water into G into L. At equilibrium, pressure at point A will be equal to pressure at point B. So P atmospheric plus density of oil into G into L plus D is equals to P atmospheric plus density of water into G into L. This P atmospheric will get cancelled out. So density of oil into G into L plus D is equals to density of water into G into L. This G will also get cancelled out. We want to find the density of oil, that is equals to density of water into L divided by L plus D. So density of oil will be, if we take in CGS, then density of water is 1 gram per centimeter cube, length is 135 mm divided by 15, that is 150 mm. So density of oil will be equal to 0.9 gram per cc. So that will be equal to 900 kg per meter cube. So this will be our final answer. In this example, we want to find the pressure of a liquid on the walls of a container filled up to height h. Let us consider a cylindrical container of radius r, so diameter will be 2r, filled with a liquid of density rho up to height h. Take a small area of the wall of container between depths x, and this will be x plus dx. This depth is dx, so total depth will be x plus dx. This area will be equal to dA is equals to 2 pi r into dx, as the thickness is dx. The pressure on this area due to the liquid is rho g x, because it is due to this height. Now the force on this area will be equal to dF is equals to P dA. So dF will be equal to rho gx 2 pi r dx. So that will be 2 pi r rho g x dx. Now the total force on the wall of container will be F is equals to integration of dF, limits will be equal to 0 to h. So force will be equal to this 2 pi r g rho will be constant, x dx limits from 0 to h. So force will be equal to 2 pi r rho g, integration of x will be x square by 2, so that will give us the answer h square by 2. This 2 will get cancelled out, so force will be pi r rho g into h square. Now the average pressure on the wall, it is the force in all the directions. So average pressure on the wall will be force upon area of the wall, that is 2 pi r. This 2 has get cancelled out, so pi r rho g h square divided by area. Area will be area of the curved surface, that will be 2 pi r h. As we want to find pressure on the wall, we will take area of curved surface. So this pi r and h will get cancelled out, so we will get P is equals to half rho g h. So this will be the average pressure on the wall. So on the base, pressure is rho g h. So on the wall, it is half of the pressure on base. Now let us see a little advanced example. A vertical U-tube of uniform cross section contains water in both the arms. A 10 cm glycerine column having relative density 1.2 is added to one of the limbs. The level difference between the two free surfaces in the limbs will be. Let us draw the diagram so that we can understand. There is a U-tube in which initially the water was poured. Now in one of the arm, initially when there was only water, the level in the two arms will be same. Now we have poured a glycerine for 10 centimeter. So the level in this will decrease and level in this will be increased. So the final situation will be something like this. Here in this limb there is glycerine, and in this limb there will be water. Now, as this system is in equilibrium, if we consider 2 points, at these 2 points the pressure will be same. Here also it is water. This length is of 10 centimeter. Let's say initially the water was at this level only, so rise in water from this side is x. So pressure at this point will be same. So comparing the pressure, so density of pressure at this point A will be equal to pressure at point B. Pressure at point A is due to atmosphere and glycerine, and pressure at point B is due to the water and atmosphere. This atmospheric pressure will get cancelled out, so we are not writing it. So pressure at A will be density of glycerine into G into height of glycerine, that is 10 centimeter, that equal to the density of water into G into height of liquid, that will be equal to 10 plus x. Density of glycerine is given 1.2. This G will get cancelled out, into 10 is equals to 10 plus x. So x will be equal to 2 centimeters. So this will be our final answer.